So hello friends, welcome back to my channel. So this is Chandu Prashant. Today our topic is design and implementation of automated car parking system using Verilog HD. So nowadays you can see in huge malls, educational institutes, organizations, and there is a very limited parking space. And due to increased vehicles, it leads to parking problems. So in order to avoid this, we have proposed this project. Okay, here the system automatically checks the availability of free slots and parks the customer vehicles without any difficulty. So here the entire project was designed using Verilog hardware description language. Okay, for that I am using the tool called Xilinx Vivado. Okay, Xilinx Vivado 2015.2 okay version. So let me explain the design code initially. See here, it is a design code. First one is module declaration. The name of the module is car parking system, and we have inputs and outputs. So inputs clock, so it will synchronizes the sequential logic, clock signal synchronizes the sequential logic. Next one reset, RST means reset signal. Next one entry sensor, so it detects a vehicle at the entry. So exit sensor, it will detect a vehicle at the exit. Next one password 1 and password 2. These two are 2-bit inputs for password authentication. So green LED and red LED. So these are the outputs actually. These two indicate the parking system status. Green LED means the vehicle can go. Red LED means it displays the error and vehicle could be stopped. And X1 and X2. These two are 7-segment display outputs. Okay, for displaying any kind of message. Next one is available spaces. These are the indicate the number of parking slots. Parked spaces. These are indicate the number of occupied slots. Vehicle counter. It is also output. It will indicate the total number of vehicles entered. Okay, it is a module declaration and input output declaration part. And next one is register and parameter declarations. See here. Here the total spaces, the total number of parking slots can be initialized to 8. Remember this. Totally we have 8 slots, parking slots, and current state and next state. These two are used to store the FSM states. And next one is wait time. Here wait time counter for waiting period. And next one is state encoding using the parameters. Okay, we have ideally, so we have 1, 2, 3, 4, 5 states. Okay, we have 5 states. 5 states are implemented using this FSM. See this FSM: ideal state, wait password state, right pass state, wrong pass state, and stop state. So we have to, our main agenda of the project is we have to implement this FSM. If we can able to implement this FSM properly, our project was done. Our project will be done. So see here. Parameter. So initial ideal state can be assigned to 3-tick P00. That means ideal state, no vehicle is detected. So all these are represented using binary numbers. Ideal state, no vehicle is detected. Next one, wait state, waiting for password entry. Right password, here password corrects, entry is allowed. Wrong password, there is a wrong password, it will entry will be denied. And stop state before the exit. So next one is next part of our code defines state transition on a clock edge. If you can see here, when the reset is high, reset the system to ideal state. Okay, or else update the current state with the next state. Okay, next one is a parking space management logic. If you can see here, if entry sensor is 1, that means if entry sensor detects the vehicle and there is an available space, so it will decreases the available spaces. Okay, and increases the parked spaces, and also increases the vehicle counter. Okay, remember this one. Similarly, just the opposite to it. If exit sensor detects the vehicle leaving and there are available parked spaces, so it will increase the available spaces. Available spaces is increased parked spaces are decreased, and vehicle counter will be decremented. So just opposite to it. Otherwise, reset the counts. Okay, otherwise reset the count. Next one is FSM state trans. So next one is a waiting period in wait state. So it is also important. Declaration of waiting period in the wait state. Okay, so it will count the time while in wait state. Okay, if wait state is active, see here, if wait state is active, so wait time can be incremented. Otherwise, it will going to be reset. Okay, if wait state is active, it will be incremented. Otherwise, it will be reset. Next, most important part of our code is FSM state transition declaration. Okay, FSM state transition declarations. See this particular FSM. So initially it is in ideal state. Okay, let me explain. With this FSM, initially a vehicle can be in ideal state. If sensor entrance is 1, okay, so if sensor detects an entry, it will goes to wait password state. That means if a vehicle arrives and the space is available, it will move to wait password state. Okay, in this state, it will wait some period. That means, for example, 3 seconds. So if the user can enter the right password, so it will move to next state, right password state, or else it will goes to wrong password state. Okay, and if the correct password is entered, for suppose, if correct password is entered, and if both entry sensor and exit sensor are high, it will goes from right password state to, if both entry sensor and exit sensor are high, so from right password state to, it will goes to stop state. If only sensor exit is 1, that means if only exit sensor is high, from right password state it will goes to ideal state. Okay, so similarly wrong password, when it is comes to wrong password state, if it is a right password, so it will goes to another state, otherwise it will remains in same state only. Okay, so stop at this stage. So if it is can enter, the user can enter the right password, it will goes to right password state, otherwise it will remains in wrong password state. Simple guys. So it is an FSM transitions. So initially ideal state, if sensor is will entry sensor detects an vehicle, it will goes to wait password state. So if the password is correct, it moves to right password state. Okay, or else it will goes to wrong password. Okay, so at the right password state, if entry sensor and exit sensor are high, it will goes to stop state. If only sensor exit is 1, it will goes to ideal state. At wrong password state, if there is a right, user can enter the right password, enters right password state, otherwise it will remain in wrong password state only. At this particular state, the user can enter a right password, it will enter to right password state, otherwise it will remain in wrong password state only. The same logic I have implemented in this code, from here to here: ideal state, wait state, right password, wrong password, stop, and finally we have to write the some default state also. That means default state means it will goes to ideal state only finally. So it is a FSM state transition. And next one is a LEDs and 7 segment display. That means output control logic. So see here. Ideal state, no lights are on, so LED displays 0 0. It will display 0 0. And in wait state, it will blinking the LED, blinking green LED, prompting user to enter a password. Okay, so at this state, wait state, the user have to enter the password. So if the password matches, so if the password is matches, it will, this particular LED will shows message called as go. So if the password does not match, incorrect password, so it will shows red light and it will shows the message called as E. Okay, so okay, if you want to stop the vehicle, it will show the message called as a P. Okay, it is a design code completely. Now we can see, so it is an complete working. So it is an working in brief: entry detection, exit detection, and vehicle. These are the main steps. Okay, and it is an RTL schematic, and it is an technology schematic. After synthesis, this particular gate level netlist can be generated. Okay, so it is a synthesis reports. If you can see this power report and utilization report, the total power required is 10.075 watts. So it is a combination of both static power and dynamic power. And the number of slice LUTs lookup tables are total available spaces. Lookup tables are 63,400. So among them used are 11. So utilization percentage is 0.02. Okay, so it is an utilization report. And if you can see the test bench code, let me explain the test bench code also. So it is an test bench code. So here I have written the test bench code. So see here, it is an test bench code. So here same. So I'm declaring inputs and outputs, and after that I have instantiates the unit under test. I mean it's a design under test. After that I have initialized the clock. That means the clock here the time period is 10 nanoseconds. Okay, for 5 nanoseconds rise signal and another 5 nanoseconds fall signal. It means the clock period here is 10 nanoseconds. And if you can able to see the simulation result, so let me run the simulation. We have to run the behavioral simulation. Let me run this simulation. So see here, it is a simulation. Okay, so let me change the radix for better understandability. So I am changing the radix to unsigned decimal here also, and here also. So see here, initially the number of available spaces are 8. So there are parked spaces, vehicle counter is 0. After that, the number of available spaces is 7. Why? Because one vehicle is parked and vehicle count is also incremented. After that, available spaces are 6. Why? Because parked now the parked vehicles are 2. Then vehicle count is also incremented, right, along with the parked spaces. Next one is available spaces are only 5. Why? Because 3 vehicles are already parked. So here the number of available spaces are 4. So why? Because already parked spaces are 4. So up to now it will initialize it up to 8 only. 8. So we have designed this code for only 8 space. So 8 states. That means 8 parking slots. Okay. Total parking number of slots are 8. Like this we have designed the code. Okay. So if the password is correct, it allows for an entry. If password is wrong, it does not allow. It will show a message. Okay. If you can see the TCL console window, so we have used the statement called as a $monitor. If you can see in the test bench, so we have used the $monitor to print in the TCL console window. So open this TCL console window. If you can see here, so the total will be the whatever the displayed in this waveform have printed here. So at time equal to 0, clock signal is high, reset is 1, and entry sensor is 0, exit sensor 0, password is 00. Here also password to 00. Like this, the total simulation result will be printed here by using the help of $monitor statement. Okay, $monitor system task. Okay. So in this way we can able to detect okay, the parked spaces. If you can see this power report also, let me open. So it is in power report. Okay, so the synthesis is running. Here you can see this synthesis is running, and okay, see here. and it is initializing the device. Yeah. Okay. See here, it will estimate the total power. So it includes both static and dynamic power. See here, running power estimation. So see this one. So the total power is 10.136 watts. That is what I have designed. So 10.136 watts. So among them dynamic power. So and it is a static power. Okay. So it is a total estimation, power estimation. Okay. Thank you.